Hello and a warm welcome to our presentation on immersive sound for electric guitar. My name is Duncan Werner. Colleagues also presenting today are Bruce Wiggins, Emma Fitzmaurice and Matthew Hart. All have made a significant contribution to the project. Our joint presentation is based upon GASP, Guitars with Ambisonic Spatial Performance. The principal aim is to reimagine the guitar as a spatial immersive instrument. It's based around ambisonics, with the actual guitars being just one component of the wider system. The project was initiated with funding from the University of Derby. The initial idea was to create a spatial musical instrument, so it would help to define a few terms. The term sound spatialization is a group of techniques for organizing and manipulating the spatial projection and movement of sound in a physical or virtual listening environment. And, in addition to pitch, timbre, intensity and duration, an understanding of space is a significant musical parameter, and as such, musical instruments with spatial sound control should be regarded as instruments of musical expression. Some guidelines for the design of a spatial musical instrument were also useful. Suggested design features include: is the spatial control made by an individual or shared by a group of performers? Is the performer exclusively controlling spatial parameters in contrast to one who controls both spatialization and sound generation? What's the required level of expertise for expressivity and virtuosity? And does the system provide a graphical user interface for real-time visual feedback? As an overview, we're bringing together a range of sound processing and spatializing technologies and applying them to electric guitar. There are two distinct but related strands to the project. Firstly, from a technical standpoint, the project investigates individual string timbralization coupled with ambisonic sound processing. And secondly, from a musical standpoint, space now becomes a performance and production parameter. The audio may be heard over a circular array of loudspeakers, preferably in a medium or large space. This would be for live performance or pre-recorded playback, for example, a theatre or concert hall. Alternatively, it can be heard over headphones as binaural sound, which would preferably include head tracking. This then also takes us into potential applications for virtual reality. Spatial production for guitar can involve requiring control over many parameters. So the idea of a live producer is conceived. That is, a person charged with control of spatialization and other performance variables. The player or live producer may have interaction with a range of performance features. For example, split timbres across strings, the selection and modulation of spatial patterns and spatial tempo, spatial arpeggiation effects across strings with Guitarpagiata, spatial timbral crossfading, and real-time performance retuning, or scordatura. We're using Reaper as our principal DAW for timbralization, spatialization, and arpeggiation. Reaper's track-channel design approach offers much flexibility for multi-channel processing, and Ableton Live provides control for the many parameters of these three elements of the system. Here we can see a routing overview across both computers. The Mac Pro is running Reaper, which is hosting plugins Helix, TrackGate, and Wigware. Each of these softwares is ×6, that's one for each string of the guitar. The iMac is running Ableton Live to provide control of the timbre, the arpeggiator, and the spatial automation. This is through Ableton Live Clips, which may also be selected through the foot controller pedals. Here's a photograph of the working GASP system. The current hardware configuration We have two interconnected computers, the Mac Pro and iMac. There's three visual monitors, one with spatializers, one with Reaper and one with Ableton. There's audio interfacing and the three guitars, two Strat type and an electroacoustic, which are all retrofitted with divided pickups. You can see 2 of the 8 surround loudspeakers in the picture. Divided or hexaphonic pickups are designed to provide access to individual string signals. So for each string, we have its full dynamic range and full bandwidth without masking effects across strings. We have 2 types, Ubertar, which is passive, and Psych-Fi, which is active. Both work very well, but have differing tonal qualities. The Focusrite Scarlett 18i20 is our multi-channel interface. This provides all the I/O that's needed. That's 6 discrete inputs, 1 for each string, plus the normal guitar output from the other standard pickups, and 8 outputs to feed the circle of loudspeakers. We work with 8 outputs for convenience. This could be more if needed. Helix Native Timbralizer. The core sound for each string is associated with an instance of line 6 Helix, providing amp simulation and many other time and frequency-based effects. So we're running 6 independent helixes, that is 1 for each string. An important point is that the output from each individual helix is stereo, or rather pseudo-stereo. This stereo output from the sound processor is a prerequisite for the Wigware spatialization processing, which we'll see later. Timbral selection. We needed some way of selecting 6 helixes simultaneously, so here we introduce the idea of timbral selection. We've created a number of timbral clips which may be selected from within Ableton. We call this the Timbralizer. A timbral clip will select 6 independent helixes. A timbral clip may be programmed to have the same sound on each string, different sounds on each string, or different sounds across groups of strings.
My name's Bruce Wiggins, and I've been involved in the GASP project as the creator of the spatialization software tools used in this project. Ambisonics was chosen as the spatial platform for the project due to its scene-based approach to content creation. The full 3D, or in this case 2D scene, is mixed to B format, which is a collection of spherical harmonics detailing the various spatial aspects of the sound scene. These can be thought of as microphone polar patterns which contain higher spatial detail as the order is increased and fully describe the sound scene to that set order. It's a flexible system that can be decoded to pretty much any format after mixing, including surround sound speaker formats or headphones, making the format future-proof. Ambisonics lends itself very nicely to headphone-based formats as the whole sound scene can be easily reorientated during the decoding, so head tracking can be taken into account. The GASP project has mixed and produced all of the audio using an octagonal 2D speaker array, and the examples you'll hear later are those same mixes redecoded for headphone reproduction. GASP currently works to third order ambisonics, which requires 16 channels to represent the spherical harmonics to this order. Horizontal only ambisonics actually utilises 7 of these, and these circular harmonics can be seen below. A decode is created by mixing together different amounts of these channels to create virtual microphones pointing in various directions and sent to loudspeakers. For presentation over headphones, these loudspeaker feeds are binauralized and summed, although the theory of spherical harmonics allows for more efficient filtering to take place, as the binauralization can take place directly on the spherical harmonics, which implements the decoding. The order of ambisonics used dictates the minimum number of loudspeakers or spatial samples needed to reproduce the sound field. As the order of ambisonics rises, the frequency of correct reproduction or spatial aliasing frequency rises, and on this slide you can see the head-related impulse responses and the interaural time and interaural level differences for a real and ambisonically decoded source over headphones. The ITD is shown from DC to 1 kHz, as this is primarily a low-frequency spatial cue, and the ILD is shown from 800 Hz to 4 kHz. You can hopefully see that the first order is correct up to about 400 Hz, and that third order ambisonics is correct up to around 1200 Hz. The next slide shows 5th and 8th order ambisonics lift the spatial aliasing frequency still further. Above this spatial aliasing frequency, there are a few techniques for further improving the decoding, which are being actively researched at a number of universities. As an aside, if you'd like to hear head-tracked ambisonics up to 15th order and with head tracking carried out by webcam facial recognition, please visit our WAM project webpage with the web address shown on this slide. The ambisonic panning software used in this project was implemented using JSFX. They're authored using the EL2 scripting language, which is compiled on the fly with an IDE built into the digital audio workstation software Reaper. The language is C-like and great for rapid prototyping and live code editing, with plugins being simple text files easily distributed with the Reaper projects themselves. If you're new to audio plugin development, it's actually a great place to start with the source code for many example plugins available in Reaper itself, including a multi-channel VU meter written by me. As mentioned, the GASP panners currently utilise third-order ambisonics, with the panner accepting a 2-channel stereo input and outputting a 16-channel third-order ambisonic output. The current panner is horizontal only, but could be expanded to full height, and I've currently got panners working up to 31st order horizontally, which equates to a 63-channel output. 6 stereo outputs from Helix are sent to the 6 panners, which allow for independent control and automation of the spread, angle and distance parameters. Angle is controlling the midpoint of the spatial image. Spread is how far away from this center point are the 2 channels of audio coming from Helix, and distance is more of a focus control, dictating how pinpoint the images are in those directions. 2 further ambisonic spatial effects are also available. The Wigware Ambi-Freeverb 2, which is a multi-channel recursive reverb engine based on Freeverb that works in the ambisonic domain and is able to take into account the position of the audio in the ambisonic field being sent to the reverb plugin. And Blue Ripple's Spatial Delay, which is an ambisonic feedback delay plugin allowing for dynamic rotation of the ambisonic sound field inside the feedback path itself.
Spatializer Clips in Ableton. To enable the selection and control for the spread, angle and distance panners, we've created a number of pre-programmed spatial patterns, or what we now term spatializer clips. Each spatializer clip contains a unique spatial arrangement. These spatial arrangements may range from simple static positioning of each string in its own space, through to complex dynamic movement and interactions of the 3 spatial elements, spread, angle and distance. We now have some visual examples. Spatializer clips. There are 7 examples of various spatializer clips to show. The others may be viewed online at gaspproject.xyz. Firstly, here, a simple configuration. You can see that each string is fixed in its own 2D space with no movement. So that's E string, A, D, G, B, E for standard tuning, and each string is located in its own 2D space around the playback circle. The Helix stereo spread is set to almost mono. That's the red and blue overlaps. That's left and right in nearly the same space. Spatializer Clips example 2. This is based on the previous slide, but now with rotational movement. For clarity, this clip and others are shown at a relatively low speed or low spatial tempo. However, the spatial tempo may be modulated externally. More on what we've called spatial tempo later. Spatializer Clips example 3. This shows another fixed position clip, and here the stereo spread on each string is wide, such that each string's stereo image is almost in its own space. Spatializer Clips example 4. This introduces rotational movement to the previous clip, which has wide spatial imaging. Again, for clarity, this is shown at a low spatial tempo value. Spatializer Clips example 5. This gets a little more involved, the key points being the angle of each string is rotating and is offset against the other strings. The stereo spread on each string is now modulated, that's the red and blue pucks, such that the stereo spread now wraps around and then back over the center point of the stereo image. Spatializer Clips example 6. Up to this point, the distance control has remained fixed. However, example 6 builds on the previous clip and now also modulates the distance element, bringing it in from the periphery to the center and back again. This configuration has an interesting spatial effect where there's noticeable movement of acoustic peaks and troughs. This is associated with the overlapping left and right spreads of the distance element. We've termed the effect spatial waves, the frequency of which is associated with the overall spatial tempo. Spatializer Clips example 7. In this last example, angle rotation is not used. Instead, there's a fixed angle on all strings, resulting in a star shape across the 3 pairs of strings. And with distance being again modulated, this creates the left and right images spreading and interacting with the other strings and causing the spatial waves effect. Spatial tempo modulation using MIDI expression. We've created the term spatial tempo to refer to what might be called the speed of movement of the spread, angle, distance spatializers. The spatial tempo may be mapped to an external controller. In this case, we've implemented MIDI expression software. This enables a physical pedal to control the spatial tempo and mirrors the pedal movement on screen. We can see here the way in which pedal changes affect spatial tempo, and for clarity, we've shown only one spatializer, although in practice this would control all 6 spatializers together. A useful feature of MIDI expression software is the variable shaping of the I/O curve, which will allow greater resolution control of particular spatial tempo bands. This will be useful for future work in investigating perceptual effects. Spatial tempo and perceptual judgments. The spatial tempo is controlled by Ableton's master tempo control, which ranges from 20 to 999 BPM. This means we can do listening test experiments over a high range of spatial tempo values, allowing us to investigate perceptual judgments and observations that relate to spatial tempo movement. Some interesting production possibilities with synchronization between programs using MIDI timecode include the matching of spatial tempo with Reaper's main project tempo, or any multiples or submultiples, including alternative time signatures such as dotted or triplet rhythms. Anecdotal feedback, interestingly, from listeners at higher spatial tempo values has included comments such as being inside the sound of the guitar. Sense of immersion. For clarity, we can see a single spatializer which represents all strings rotating together without offset and having a varying spatial tempo. In this example, at the lower spatial tempo values, listeners have commented they can comfortably follow the movement of the sound location. However, for higher values of spatial tempo with the same pattern, listeners have then commented on perceiving a fuller sense of immersion. If we compare the previous slide with this one, which is the same pattern as we saw in example 6, it's clearly a more complex spatial pattern, and listeners have commented for this pattern at the same spatial tempo as previously, there is a different perception of the degree of sense of immersion. However, we've yet to define descriptors for what different means, so we really need a lexicon of terms, something like the sense of perceived spatial immersion. In this example, the distance element is being modulated and, as mentioned previously, creates an interesting spatial waves effect. Guitarpagiata. The Guitarpagiata creates an arpeggiation-like effect. It's based upon the idea of switching individual strings on and off in a rhythmic fashion where each string has its own on-off pattern. Each string is assigned a MIDI note value which controls the opening and closing of an audio gate on that string. So for example, we have a MIDI clip here from Ableton where there are 6 note values which are each assigned to a different string. And in this clip we've got some MIDI note on and off blocks, and these represent the audio switching on and off of the audio gate. And in Reaper you can see the signal coming through on each string according to when this note was being switched on or off. The audio gate we use is DMG track gate. This, in conjunction with MIDI note on-off patterns, enable any sustained chord to have on-off switching of individual strings. This enables simple or complex arpeggiation-like effects. Like timbralization and spatialization clips, we've created around 20 Guitarpagiata clips with various patterns of rhythmic switching, some of which have been based on the timings of drum fill patterns. The Guitarpagiata's rhythmic effect is heard during the decay, sustain and release phases of each individual string's ADSR envelope. The effect works well with timbres that have long sustains. Here we see a screenshot of Helix's Secret Travel. This has 8 serial delay lines to enhance the sustained duration. Additionally, the arpeggiation-like effect may be mixed with the output from the standard mono guitar pickup, giving a more blended effect. An interesting outcome occurs when cross rhythms and non-standard time signatures begin to emerge. This occurs when the player's rhythmic performance purposefully interacts with the arpeggiation switching sequences, thus creating a sort of performance feedback loop. Future work includes investigating plugins to auto-generate random but rhythmically useful arpeggiation patterns. Here we have a screenshot from Ableton showing all of the Spatializer, Timbralizer and Guitarpagiata clips. The combination of any of the 3 types of clip may be aligned together to form a GASP scene. For live performance control, a Behringer pedal board may be used to select timbral, spatial and arpeggiation clips stored in Ableton. The variable expression pedals are linked to the Spatial Tempo value, which are associated with the Spatializer movement and Guitarpagiata's audio gate switching rate.
Hello, I'm Matthew Hart. As part of the GASP project, my work is primarily focused on integrating Helix Native into the system. An area of the project that we've been investigating recently is the idea of real-time retuning. This is something that could be valuable for guitarists who intend to change tuning within a performance, whether that is within a single song or between songs in a setlist. We're investigating 2 different ways of realizing this, the first of which involves a system that switches between several discrete alternative tunings. The second involves morphing gradually between tunings over a period of time, and the latter of which is aimed more towards experimental contemporary performers. We use the term scordatura in this context, which means tunings that are different from the normal standard tuning. Here's an example of the signal path for our real-time retuning approach. So first we take the signal from an individual guitar string, then we route this into a first instance of line 6 Helix, where we apply pitch shifting, After this, we route it into a second instance of Helix Native, where we apply amp simulation and effects processing. This stage we refer to as timbrization. Then we route this into our GASP panner plugin, which we refer to as spatialization. This whole signal path is applied separately to each string, which means we have 6 duplicates of this signal path. The benefit of us having 2 separate instances of Helix here is that it means we can apply pitch shifting completely independently of whatever presets we might want to use for timbrization. For the discrete retuning approach, we've decided on 8 tunings we intend to switch between. This table shows how we can achieve these tunings using different amounts of pitch shifting on each string. To have the guitar in standard tuning, we simply apply no pitch shifting to any string. If we want to switch to a drop D tuning, we simply need to apply a -2 semitone shift to the low E, which creates a D note. The other tunings involve more pitch shifting, and it varies more between each string. For example, our third tuning, open D major, involves a -2 semitone shift on the low E, creating a D. It involves a -1 semitone shift on the G, creating an F sharp, a -2 semitone shift on the B, creating an A, and lastly a -2 semitone shift on the E, creating a D. In order to achieve the pitch shifting we require, we use pitch shifting blocks inside of Helix, which we control using Helix's snapshot system. Snapshots allow for up to 8 variants of the same preset to exist. Within each of these snapshots, we can specify the tuning parameters for the pitch shifting blocks on that preset. An individual instance of Helix on each string contains a pitch shifting block and 8 snapshots which we've created that are unique to that string. Because of this, we can apply separate pitch shifting to each string. For the discrete switching approach, we use the simple pitch block on each string. We adjust the interval parameter, which equates to a semitone pitch shift as required. In order to switch between the snapshots we've created, we can use a value between 0 and 7 on MIDI continuous controller number 69, which is pre-mapped in Helix to correspond to the snapshot setting. This message can be triggered either using a programmed CC message in the DAW, or we can manually trigger it using a foot pedal. This method is quite convenient because it means we can use a single CC message routed to each of the strings to simultaneously control the tunings of all of them. The second method for retuning involves a continuous approach. Instead of us immediately jumping to a new tuning, we gradually alter the pitch of the string over a period of time. This technique is aimed more towards experimental contemporary guitarists. For the continuous retuning approach, we use a Helix pitch wham block on each string. The pitch wham block emulates a pitch shifting expression pedal, where the position of the pedal corresponds to what pitch shifting is applied to the signal. This enables us to achieve smooth pitch morphing, as it doesn't snap to semitone values. To control the pitch shifting applied by the pitch wham block, we can modulate its position parameter. We can achieve this by either using a Reaper automation lane or a MIDI CC curve, which can be assigned to any unused CC number. This screenshot shows an example of how we might apply pitch morphing across a period of about 2 to 3 minutes. Another area of the system involves post-production of existing recordings using our GASP processors. This involves using software to separate individual notes from existing recordings into several channels in Reaper. This allows us to individually process each of the channels. To test the idea, we've used the track Gone Sailing by Soft Machine. This is an instrumental acoustic guitar piece performed by Alan Holdsworth from the album Bundles. First, we take a WAV file of the track and import it into Reaper. Then we process it using Celemony's Melodyne software. Melodyne has a feature known as Direct Note Access, or DNA, which extracts individual notes from a polyphonic recording and enables the user to visualize and edit notes. This feature is more often used to apply pitch editing or time editing, but we are using it in a slightly different way in our system. This screenshot shows an example of the data Melodyne calculates for the entirety of the track gone sailing. We are able to edit any of the notes shown here. At this stage, we now need to determine how we would like to group the notes into 6 different tracks. This screenshot is color-coded, with each color resembling notes that would appear on an individual string. Now that we've decided on how we want to group the notes into strings, we can use Melodyne to separate the notes into several different tracks. In order to achieve this for a single string, we simply need to use Melodyne to mute all the notes from any string other than the string we want, leaving the notes from the string we want unmuted. Now we can process this audio just as we would a recorded guitar string, so it can have its own spatializer. Next, we just need to repeat the extraction process 6 times to leave us with 6 different audio tracks, each resembling a single guitar string. It's now possible to apply GASP processing to the separated tracks in order to create an immersive sound mix.
Hi everyone, I'm Em Fitzmaurice. I'm going to talk a bit about the GASP2 project that we've had going on. So, while we've had the original GASP system for a while now, and it's kind of proven itself to be quite versatile, we did want to have a go at creating a new system based on what we've learned over the last few years. First goal for this was to reduce the hardware requirements. So that was kind of a big barrier with GASP1. We used 2 computers and 3 monitors and a bunch of hardware. We wanted to bring that down. So now it's all running on 1 computer, 1 multi-channel interface. Good to go. The other part was to rework the control system. Been using Ableton, want to try some other stuff. I'm going to go into a bit more detail on that. When we're looking at our options for a different thing to do, we did consider sticking with Ableton, looking more into Max for Live. Probably could have gone further with that, but been a bit awkward. So could have made something bespoke in Max or PD, probably. That was just to be the control system for this. But to get the clip recall and all that was kind of at the core of it would have been a bit of a faff. We still looked into Playtime, which offers Ableton-like clips within Reaper itself. So we could combine it into kind of a single software package. But they don't play well together, having the audio and the CCs kind of out of sync with each other, because they try and stick to the same timeline. The ultimate solution that we decided on was Bitwig Studio. So Bitwig, as Ableton was, is massively overspec'd for what we're doing. It's a full-on DAW. You want to make music, but the thing that's special about it is the modulator devices. They're like little plug inlets. There's LFOs and envelope followers and envelope generators and all this stuff it's used with modular synths or with plugins, but it can also kind of stick it out as a MIDI CC. So essentially this is the interface for that. You have this kind of setup on each string. So on the left in the green box, we have 3 instances of the LFO device, classic LFO device, which is assigned on the right in the orangey peachy box. And the interface for that is in the blue box in the center. So here we have frequency first. So we could tempo sync that, or we can have it free running. This is independent for each oscillator and each string. So you want it to spin around at a certain speed and then dip in and out at a slower speed. We can do that, which was a right hassle in Ableton. We have amount, which is essentially the depth of the LFO. So if you want something to kind of wiggle left or right a little bit, we can keep that low. If we want to wiggle left and right massively, turn that all the way up. Or to do full loop-the-loops, we turn that all the way up as well. Phase is really useful, so we can have things slightly offset on each string. So if we want to have 2 strings chase each other around, or have all 6 chase each other around, then we just kind of split that phase up between the different strings, keep everything else the same, and they'll do the same motion, kind of lagging behind each other. And then we have wave shape. So it's the standard sine and triangle for wiggling square for kind of bouncing. Sawtooth will do full loop the loops on the angle, because essentially 360 becomes 0 and then works it all the way back up again, vice versa if you want to spin the other way. And then there's some cool sample and hold and random stuff that we've not really looked into yet. So in the pink box here, you have some other devices. Again, these are more things to experiment with, really, which is kind of one of the joys of this new system. Is it's much more playful than the previous one. So this CC1 is an external controller, so you can control the rate or the amount, or basically any parameter from an expression pedal. So while you're playing, you can have it speed up how it's moving, or slow down, or get more dramatically pulsy. Second one is a quantized form of one of the LFOs. Tried that out. So now that would make it step around in discrete steps as opposed to being kind of continuous, or at least 127 steps of continuous. It's more like 6. And then this is a mixer to mix between the quantized steps and the continuous wave. There's loads more in here that we kind of haven't got to playing with, but it's a kind of interesting opportunities await in there. And that's basically the layout. With one of these for each string, all the parameters of these devices are stored in clips. Trigger the clip, recalls all the parameters, you're good to go. Much easier to make than the Ableton ones. Thanks.
Future work 1. To generate further audio examples demonstrating features presented to ADC today. Examples of Guitarpagiata, RealTime Retuning, spatial remixes and others are being generated and uploaded to gaspproject.xyz. 2. To investigate applications other than guitar, for example, any two musically related signals may form the input to the spatializers. And whilst we've focused on the guitar as the spatial instrument here, we plan to investigate the spatialization of other instruments or groups of instruments using the techniques outlined in our presentation. And 3, we welcome interest from graduates in music or music technology, or guitarists who may be interested in exploiting GASP as a compositional or performance tool. The University of Derby's College of Arts and College of Engineering have a great symbiosis in spatial audio research and application. Future work 4. To expand the current 2D circular implementation to enable height information for 3D spherical representation. This will involve reimagining GASP's spatializers with embedded Z-plane information. 5. To investigate the implementation of GASP within Dolby Atmos, as this is now supported within Reaper. Dolby Atmos supports height information, but not in the same way as Ambisonics. However, the integration of Atmos rendering in Reaper opens up interesting possibilities. 6. To design and implement listening tests to measure the degree of sense of perceived spatial immersion experienced by listeners. We mentioned this in our presentation, and this work would require some form of lexicon of spatial perception. Future work 7. We have a portable GASP rig, including a circle of loudspeakers, and can offer live demonstrations, presentations, workshops, etc. to any interested parties, music colleges, guitar schools, universities. We'd be happy to demonstrate the system in a real space. Do get in touch if this is of interest. And finally, GASP system standalone development. For some time now, we've considered how a standalone version of the system might be conceived. If you're a hardware or software audio engineer or a student in these fields with an interest in the project, do get in touch, even if it's just for an informal chat. Some example demonstrations. These demonstrations were originally mixed on our Ambisonic 8-speaker circular array and intended to be heard over a similar system. However, for this presentation, they've been converted to binaural sound to be heard over headphones. 3 examples follow, each one around 1 minute duration. The first 2 tracks begin with the raw mono guitar and then crossfade into ambisonic binaural production.